Okay, we're getting ready to kind of finish off chapter 1. I know that I've gone into sampling in a lot more detail than our textbook goes into it, for good reason. If you're really doing a statistical study in real life, probably 90%, 95% of the time spent on that study, 90 to 95% of the money spent on that study, it really goes into that sampling process. Also, we saw that if you sample properly or improperly, it makes a huge difference in terms of whether the ultimate results are valid or invalid. An introductory statistics class, it can give you a distorted view of statistics. That is, we're going to spend 95% of this class sort of assuming that we've taken a sample. That is, someone just hands us some numbers, and we're going to learn a whole bunch of cool tricks and ways to manipulate these numbers. That's well and good. And you can always do that. I can give you any numbers, and you can apply the statistics that we're going to learn in this class to those numbers. However, if those numbers are coming from a sample that's done improperly, if the numbers are coming from a sample that's not random, from a sample that's not biased, the conclusions you're going to make are distorted or they're wrong. If the numbers that you're given are junk, then the conclusions you're going to make about them are junk as well. And so that's why the sampling process is such a critical process in terms of overall statistics. Not just implementing a study, but you as a consumer trying to read a magazine, to read a research article, to read a newspaper. The number one thing that you want to be critical about is how did they take the sample? Where did the numbers come from? And were they selected in such a way that maybe something like bias could have been introduced into the picture? So I think it's important to spend at least a little bit of time going into the details. I mean, like I say, we could do a whole class. I do an entire class just on the material that we talked about. So we're still just scratching the surface. But it is important material that I want you to be aware of, and some big picture ideas that I want you to be comfortable with. Now, to finish off the chapter, we're going to talk about two different types of studies. But before we do that, I want us to make a distinction between two different types of variables. Actually, three different types of variables. This distinction is actually going to come back, I guess, to haunt us in Chapter 9, so it's good to get a little bit of early exposure right now. Now, sometimes statisticians wish to see whether one variable influences another. That is, they wish to see if an explanatory variable explains another variable called the response variable. Sometimes we think of that explanatory variable as like x, which makes sense, right? Because the letter x is in the word explanatory. And we think of the response variable as y, right? Which makes sense because the letter y comes after the letter x. Now, variables other than the explanatory variable that might also influence the response variable, these are known as lurking variables. Now, there's two types of statistical studies. One is what we call an experiment. An experiment is a situation where a treatment is deliberately imposed on the experimental unit or individual to observe a possible change. An observational study is where observations and measurements are made without influencing the response or variable being measured. Right? So the experimental study, there's sort of this active involvement by the statistician or the researcher. Observational studies are sort of like letting nature take its course and just observing what happens afterwards. So here's some examples of an experimental study. Right? Here's the classical sort of clinical trials example. Two groups of people are randomly assigned. Some are randomly assigned to take medicine A. Some are randomly assigned to take medicine B. We have some students, and we break them into two groups. We randomly assign some students to take Math 121 online. We randomly assign some students to take Math 121 in the classroom. Ooh, here's a baking example. We take some cakes. We randomly assign some cakes to say 400 degrees. We randomly assign some others to say 425. We randomly assign the rest to 375. Right? All of these we have this sort of random selection process. Oh, and this deliberate imposition of treatments. Contrast that with an observational study. So an observational study might be like this. We might go out and we might gather data regarding the eating habits of early American settlers. Right? We're not imposing any treatments there. That is, we're not randomly assigning people to be early American settlers. We might look back historically at grades from 2007, spring, from some Math 121 students that took the class online, and then also some grades for some students that took it in the more traditional classroom. And the third one is heart disease is compared between vegetarians and non-vegetarians. Do we see the difference between these? Right? I'm not randomly assigning some people to be vegetarian and randomly assigning some to be non-vegetarian. Right? That contrasts with what we saw in the previous slide. In the previous slide, right, with the medicine, we assigned some randomly to medicine A, we assigned others randomly to medicine B. Right? In the first example, we're telling people what group to be in. In the second example, in observational studies, we are not telling them what group to be in. We're letting them decide naturally what group they want to be on, and then we're recording the information. So let's do an example. Say a study from hospital records found that women who had low weight gain during their pregnancy were more likely to have low birth weight babies than women who had high weight gains. My first question is this. Let's actually start with this. What's the explanatory variable? What's the variable that's doing the explaining? Good. The explanatory variable in this case is the weight gain of the pregnant mother. What's the response variable? The response variable is the birth weight of the baby, right? Our study is trying to determine whether the weight gain of the mother in some way explains the birth weight of the baby. Now, what are some possible lurking variables, right? Remember, our lurking variable is any variable other than the explanatory variable that might also explain the response variable. Can you think of any lurking variables? It's a lot, isn't there? I mean, something like diet, for instance, right? There might be differences in diet between the mother that might also impact the weight of the baby. Other conditions, how long their pregnancy was, right? These are all other variables that, in addition to the amount of weight that the pregnant mother gained, might also explain the birth weight of their baby. Those are called lurking variables. Oh, and is that experiment or observation? Good. That's an observational study, right? Because we're just letting nature sort of follow its course. We're certainly not assigning some women to be low weight gain and other women to be high weight gain. That would be infeasible, right? That would be difficult, if not impossible, to do. So even if it's not spelled out, I guess it is spelled out because we're looking back at hospital records. So we know we're looking at something that's already happened. Hence, it has to be an observational study. What about this one? A study monitors the occurrence of heart disease over a 5-year period in men that are randomized to eat high-fiber or low-fiber diets. Is that an experimental study or observational study? Good, that's experimental because, right, well, the word randomized is there. That idea of randomizing is we're assigning some men to high-fiber, some men to low-fiber. Now, whether or not people are going to stick with the diet we've randomly assigned them to, that's a whole other issue. That's called adherence, whether or not they're going to adhere to what group you've put them in. But the way it's described is certainly an experimental study. Now, what's the explanatory variable? Good. The explanatory variable is essentially their diet. The explanatory variable is whether it's high fiber or low fiber. What's the response variable? Well, it's left a little vague, but it's some measurement of heart disease, right? Maybe it's the number of heart attacks. Maybe it's the number of myocardial infarctions. Maybe it's the amount of plaque buildup. Maybe it's something like their blood pressure, right? Can you think of any lurking variables? Right? Lurking variables, remember, are any variable other than their fiber diet that might also explain their heart disease. There's a lot, isn't there? What might you say? You might say whether or not they smoke might have something to do with their heart disease. Whether or not they exercise may or may not have something to do with their heart disease. Whether or not they drink alcohol may or may not have something to do with their heart disease. There might be a genetic predisposition, right? These are all lurking variables. These are all variables other than the explanatory variable that also could influence the response variable. Good. Do you feel like you have a grasp, hopefully, of these three types of variables and being able to distinguish between an experimental study and an observational study? Hopefully you do. Now, what's the idea or what's the purpose to an experimental study? Well, an experimental study works like this. Because of the randomization used to impose the different treatments, we can assume that groups are roughly identical in regards to all the variables except for the only difference between them is the treatment of interest. This allows statisticians to draw what we might call cause and effect relationships. For instance, we might be able to say that online learning causes better or possibly worse, right, grades. Does this make sense? Let's go back to the example I think I had a few slides ago. Let's say that we're interested in doing a study looking at whether a vegetarian diet, so that's going to be our explanatory variable, has any effect, any impact on heart disease. That's our response variable. There have been lots of studies that have done this. Now, the question I want to ask you first off is, there's been a lot of studies looking at this. Do you think those studies are observational, or do you think they're experimental? Yeah, I agree. I think that they're going to be observational. Don't you agree? It would be very difficult to take some people and randomly assign them to be vegetarian or non-vegetarian. That is, to tell somebody that you know, I know you love meat. I know your favorite thing to do in the summer is to grill up some steaks or some burgers or some hot dogs. I hate to ruin your 4th of July, but for the betterment of science and statistics, I need you to be a vegetarian for the rest of your life. Sorry. Right? Or the other way, to tell someone whose maybe religion, right, forbids them to eat meat, and say, hey, I know that you have a strict religious belief that says that you shouldn't be eating this meat, and it's possible that this may send you to hell, but despite that, it's really important that you eat steaks and hamburgers and hot dogs on a regular basis for us, please. That's a lot to ask, isn't it? And because of that, these studies have to be observational. Well, so what? Well, remember, we have these lurking variables. The lurking variables are actually the same as the previous slide, right? Our response variable is heart disease, and so we have the same lurking variables. What also, besides the presence or absence of meat in your diet, what also explains heart disease? Things like diet and smoking, genetics, alcohol consumption, right? Other aspects of diet. You could still be a vegetarian and eat Cheetos and Oreos, but maybe you shouldn't be. And so imagine this happens. Imagine a study is done, and at the end of the day, it concludes that, well, people in the vegetarian group, they had a higher level of heart health. You might be tempted to say, okay, a vegetarian diet causes a healthier heart. But a devil's advocate could say, whoa, wait a minute, that's not necessarily true. Why not? Because it could be that people, remember this is an observational study, it could be that people that chose a vegetarian diet also tended to exercise more. That maybe people that choose a vegetarian diet tend to smoke less. And maybe it's not so much the presence or absence of meat that's influencing heart health. Maybe it's smoking. Maybe it's exercise. And maybe it's these lurking variables that are impacting things. This is where the experimental study is so powerful. Because of the experimental study, if you could randomly assign some people to be vegetarian, if you could randomly assign some people to be carnivorous, what would happen? Well, by the process of randomization, you would have some couch potatoes in both groups. You would have some fitness buffs in both groups. You would have roughly the same percentage of smokers in both of your groups if this was done randomly. The only difference between your groups would be, well, one group eats meat and the other group does not. And because of that, if in this experimental study you saw that vegetarians had greater heart health, then you could conclusively say that the presence or absence of meat, I guess in this case the absence, leads to a healthier heart. Does that make sense? That's why experimental studies are generally much more powerful than observational studies. Now, you can take other variables into account with observational studies. That is, and this is what's done in practice in these studies, you can also record whether the person was a smoker or not, how much they smoke, whether or not the person exercised, how much they exercise, right? Whether or not they have a family history of heart attacks, in some way quantifying that family history. You can take these lurking variables into account. In fact, you see that in reports. It might say something like, after controlling for smoking and other aspects of diet and exercise, we still saw that vegetarians tended to have healthier hearts. So there are statistical ways of addressing this and making observational studies a little bit more ironclad, a little bit more foolproof. But what makes experimental studies so great is that this process of randomization, it removes the effect of all lurking variables, regardless of whether or not you've thought about what those lurking variables are. To be able to address them statistically, not only is it more complicated, not only does it involve more difficult statistics, but you have to be able to think of the lurking variable ahead of time, and if you don't, you're out of luck. So imagine you did the vegetarian study, and maybe you took into account diet and exercise, other aspects of diet, exercise and smoking, but at the end of your study someone says, well, why didn't you take into account alcohol? Maybe that lurking variable makes a difference. And then you're left saying, well, I wish I had done that, but it's too late now. Right? In an experimental study, it's never too late. And that's why it's such a phenomenal type of study. Now, by now, you're probably pretty excited about experimental studies, and you're asking yourself, man, well, why isn't everything an experimental study? Well, we've kind of already seen the answer to that, haven't we? For one, in cases of studies on historical topics, it might be too late, right? The American settler example. You can't randomly assign some people to be American settlers and some people not to be early American settlers. In some cases, it's unethical, right? We talked about with the vegetarian example. Randomly assigning somebody to extreme diets is probably not ethical. It's probably not feasible. Randomly assigning some people to be religious and not religious is probably not ethical, probably not feasible. And also other things, right? Randomly assigning certain sharks to some habitats, again, that's probably very difficult, if not impossible, to do. So there certainly are. There's lots of examples in life where we could get stronger conclusions if it was experimental, but the circumstances surrounding it simply do not allow it to be that. Another thing about experiments is they're not always perfect. They have their own little problems and quirks associated with them. One potential problem with experimental studies is what we call the placebo effect. The placebo effect is this really crazy psychological phenomenon that occurs when a subject receives, I shouldn't say this, they receive no real treatment, no active treatment, but incorrectly believe that they are getting active, real treatment, and they respond favorably. That is, what studies have shown is you can give people with a cold, for instance, like myself, you can give them sugar pills, right? You can give them something that's really chemically no different than a Skittle. But you tell them, right? You tell them, hey, I'm a doctor, and hey, the Skittle is medicine, and they magically start to feel better. They magically start to feel better. They have an alleviation of symptoms significantly faster than people who aren't given Skittles by doctors. Now, are Skittles actually really medicine? No, of course not. It's this placebo effect. It's the power of positive thinking. That if the mind starts thinking, hey, I'm being treated, the body starts to react as if it really is. And so what we have to do is we have to in some way compensate. Statistics has to address this idea of a placebo effect, because you can't compare your medicine to just no medicine at all. That is, you can't give your medicine to some people and give other people no pills at all. Because if at the end of the day it shows that your medicine is better, a devil's advocate would come back and say, well, yeah, if you give people Skittles because of the placebo effect, they're going to get better faster than people that you aren't giving Skittles to. And so what you have to do statistically is when you compare two groups, if you have a new medicine, what you do is you randomly assign people to two groups. In one group you give them the real medicine, and in the second group you have to give them the fake medicine. You have to give them what's called the placebo. The placebo is what we call this fake medicine. So you compare real medicine to placebo. You compare real medicine to fake medicine. Because of the placebo effect, it is not valid to compare real medicine to no medicine at all. Or real medicine to no placebo is maybe a better way of saying that. Now, here we go. We fix it by creating a control group. Right? This is just a group we compare to the group that's really getting the medicine. We sometimes call that group the treatment group, by giving them a fake medicine called a placebo. This thing is so powerful, this placebo effect, that most of the time an incredible amount of care and attention is put into making sure even nurses and doctors don't know which patients are receiving the real medicine and which are receiving the placebo. These experiments are called double-blind. Double-blind because not only does the patient not know whether they're getting a real medicine or not, but the doctors, the nurses, their caretakers also do not know. Why is that? Well, lots of studies have shown that all humans tend to sort of react towards expectation, even doctors. And that doctors and nurses have sort of a tendency, if they know that someone is on a real medicine, and they look at something that has a subjective diagnosis, and it turns out there's quite a few things that do, X-rays for instance, and they look at an X-ray and they're trying to decide whether a tumor has improved or not improved, and it's sort of borderline. That doctors, if they know you're on the medicine, they're impacted by psychology as well, and they have a tendency to say, well, I know this person's on this medicine that this pharmaceutical company has pumped millions, maybe billions of dollars into, and this medicine is chemically pretty impressive, and it's really similar to this other medicine that I know works, so yeah, probably this tumor has gotten better. Right? And on the flip side, if they know the person's not on the medicine, they tend to look at these X-rays and they say, well, it looks kind of close, but there's no way it could be getting better because this person's just taking Skittles, and Skittles don't improve cancerous tumors. And so to prevent this from happening, to prevent the doctor's psychology from playing an inadvertent role in the study, it has to be double-blind. I have a question for you. Do you think it's important to use a placebo on rats? I know, it's almost insulting your intelligence. It's a silly question, but imagine that we're testing a cold medicine on some rats. And so we break them into two different groups. We're going to give one group the medicine. Since they're rats, we can't really give them pills. We have to give them a shot with a syringe. Do you think that we need to give like a fake shot to the other groups of rats? They would do that with people. In people, they do shots of like saline solution, just salt water, to sort of mimic the effect of getting an actual shot. But do you think we need to do that for rats? A lot of times people say no, that's silly, and it is right. It is silly to think of it as the placebo effect. But the placebo effect has an evil twin that a lot of us don't know about. It's called the nocebo effect. It's true. You can look it up. The nocebo effect is basically, it's the opposite of the placebo effect. Placebo effect, I think, is Latin for like I will please, and the nocebo effect is Latin for like I will harm. And the nocebo effect is like the power of negative thinking. Like, imagine this. I mean, do rats really, like, think, oh, this is comforting, I'm getting medicine, I feel better already? No, that's a silly thought. But what about the opposite? Like, imagine you're a rat, and you're just sort of hanging out, enjoying life, getting your rat thing on, and then all of a sudden, this big glaring light turns on, and this hand of God descends into your home, and sort of removes you, pulls you away from your family, from your friends, from all the rats that you've grown up with and love, and pins you down on this cold metal table. It's like an alien abduction, right? And you get this injection. It's like alien probing, and you're confused. You don't know what's going on, and then all of a sudden you're sort of put back in your crate, and you probably don't feel, oh, this is great, I've been medically treated. You probably feel the opposite, right? You probably feel violated in some sense, right? And you might feel stressed out. And certainly, right, even though rats don't have the same psychology, right, they probably do have a similar biology, in the sense that for humans we know stress is bad. Stress impacts the immune system. Why wouldn't it for rats? So probably you would want, if you wanted to make scientifically valid conclusions, you would want to give a shot to both groups. For slightly different reasons than you do for humans, but at the same time similar, right? It's that power of psychology. It's just, here we're trying to compensate for a negative or adverse reaction, psychologically speaking. What about plots of land? Say you have a fertilizer that you want to try out. Do you think you need to fertilize some plots of land and then fake fertilize other plots of land? I don't know. I mean, certainly the land's not going to react in a positive or negative way. Probably. You do want to be careful. Well, let's think of it this way. In every study, there's a human being involved somewhere. If they're not getting the medication, they are out there evaluating the effectiveness of the medication. And it's going back to that idea of double blind. If the person evaluating how successful this fertilizer is, if there's any amount of subjectivity in the measurement they might give, then you very well might want to in some way plow or till or make it look as if these other plots of land have possibly been fertilized, if for no other reason than the person that's making the measurements, that's recording the success of the fertilizer. We don't want their own psychological expectations to get in the way or to bias the results of our studies. Does that make sense? This placebo effect is really powerful, and again, a huge amount of money and time and research goes into sort of addressing and talking about this issue.